It's a Saturday evening, my girlfriend is out, my dog is asleep, so let's do a BERT tutorial. Okay, so I'm gonna try to do this as fast as possible because there's quite a lot and I just left links all over the notebook and you can check those things separately after the video or during it. The thing is, at the end of the video, what I want you guys to do is just go to Twitter, copy a random tweet, preferably from Trump, come back here, paste that tweet, get an answer if it's positive or negative. In this case, it's a negative one. So Sleepy Joe Biden is proposing the biggest tax hike in our country's history. Seems to be negative. If you agree with that, slap a like. If you don't, just argue with me in the comments down below. So what we are using here is Google Colab. We use this for both logistic regression and simple neural network tutorials that I uploaded for the last 2 weeks. If you want to watch those, and I highly suggest that you do, I'll leave a playlist link somewhere around here. The Colab itself, it's a Jupyter Notebook server on the Google Cloud, which you can access through your Google Drive at any time from anywhere, as long as you have internet. And it's a great way to start learning machine learning, since you don't need to set anything up. You can just come in here, run your code and see what it does. If you want to know more about Google Colab, here's a video as well. So, our notebook. We have imports, we have our data for training, we have the modal part where we set up the model, and then we have essentially the test part, which I just showed you. So for the imports, we start with installing a couple of packages. Since we are using BERT from TensorFlow Hub, so already a trained model, which we're gonna fine-tune today, we need to install TensorFlow Hub. And since we are using Google's BERT model from TensorFlow, we need to install TensorFlow models as well. Having said that, here is our imports. They are vastly different from the ones that we used for the simple neural network tutorial and for the one that we used for logistic regression, just because of those additional packages that you're gonna use. At the end of the importing, I added, not my code, taken from the internet, a check if you have a GPU available to you. And if you see here that GPU is not available, then it means that you need to change your runtime and you need to change it to a GPU one. As I said, if you're first time using Google Colab, go watch the Google Colab video, it explains it in a bit more detail. So after the imports, we want to read our data and prep it for training. We're gonna use the same data set that we used for the last 2 tutorials, so sentiment 140 from Kaggle with 1.6 million tweets. It already has 1.6 million tweets annotated, being either positive or negative within the target variable. What I want you to do is to download the dataset, then open up my notebook, which I will leave in the description down below with all the other notebooks. So the logistic regression, simple neural network, this one for BERT, and a modified BERT as well. So after downloading data, you need to upload it to your Google Drive to use it for a notebook. And just change this path right here to the one which is your own from your own Google Drive, and then just read data and print out the first couple of lines. We do that just to check if the data was read correctly, what are the variables, how the data looks. So we see that we have a couple of variables here, namely the ones that we are interested in are target and text. Target being the sentiment, so is a tweet positive or negative? And if it's a positive one, it's a 4, and if it's a negative one, it's a 0. And the text, so the text of the tweet, which you're gonna use to predict that same sentiment. So if you would check out the amount of classes that we have, so the sentiments, you'll see that we have a 0 and a 4. I get it, when you have a 0 and a 4, you expect to have something between that, like a 2 for neutral, but you don't, so we're just gonna stick with that. Before any classification, you want to check if the classes are equally distributed. So you see that Yes, indeed there are. Both negative and positive tweets are distributed equally within the dataset. Why we want equal classes within the dataset? Well, just imagine a situation where we have 95% of the tweets being negative and just 5 positive. At the end, what you will get, a model which is depressed and says that every tweet you input to it is a negative one, and we really don't want to have that. So to start modeling, we need to do a couple of things. Split the data into training and testing subsamples. We need to encode our labels, so our classes, and we need to tokenize the text within the tweet. So we're gonna start with splitting the data, and for training we're gonna use only 5% of all of our data. Why? Well, for one, we have 1.6 million tweets, so that's quite a lot of tweets, and it would take quite a lot of time to train on all of the dataset. And the second thing, we don't really need that much data. 5% should be quite enough here to train our model for a couple epochs and get at least the same result that we had with simple neural network, where we used 10%, and logistic regression, where we used all of the data. So having said that, yeah, we split the data set into training and testing. We needed the testing one to check if the model actually is training on the patterns within the data and not just remembering the data itself. And without a testing sample, that wouldn't be possible. After the split, we need to encode our labels, so our sentiment. What this does, it just checks what the unique classes within our sentiment are, and then transforms that variable into indexes of the classes instead of the values of the classes themselves. We use one-hot encoding here, just because I figured that you might want to use this notebook for multi-class classification, where there is 3 or more classes. With binary classification, you could actually do it in an easier way, but I wondered this notebook would be reusable for you, so we are sticking with one-hot encoding. Now I'm saving the encoder here, just because we're gonna use it later on for fine-tuning our model a bit more after initial training, and because we already did use it in the testing side. Here we read our encoder to load the classes variable of that encoder to see what are the indexes of the classes. So having said that, let's move to tokenization. So differently from the simple neural network that we did last week, BERT needs not one input, but 3 inputs. One of those inputs is pretty much the same as with the simple neural network, so tokenized tweets, where you just get arrays of token IDs instead of tweets themselves. The second input is the input mask, where we just show the model where the inputs actually are. And the third input is the input type. We don't really have multiple types here, so segments like one sentence and the other. So instead we just show the model where the actual inputs are and not just some tokens as classification or separation. So first, before tokenizing anything, we actually need to download the model itself. If you want to read about BERT models, I suggest you go to this link here. If you want to read about the model specifically that we are using, this is the link for that. So as you can see, we are using a model from TensorFlow Hub, and our model is BERT Multi, which stands for multilingual. So the model is pre-trained on more than one language. If I remember correctly, it's 112. Cased takes into account if the words were uppercase or lowercase. So you can read more about the model here in the link provided, and you can check all of the TF Hub models in this link. For those of you who don't really know what TensorFlow Hub is, it's a hub for already pre-trained models which you can use and fine-tune to solve some problems that you might have, so such as text classification in our example. This is what you're gonna do as well. We are downloading a model, we are setting that it's trainable just because, well, we're gonna train it. So after downloading the model, we need to read a couple of variables of that model, and those being the vocabulary file and the lowercase variable. So since our model is cased, that means that it takes into account if a letter is upper or lowercase. You can check that variable after reading by just printing it out, and you can see that it's false. You can see that describes right here in the text box after this cell. Another thing that we are reading is the vocabulary file. We are not building a vocabulary as we did with our simple neural network tutorial. We are reading the one that is already there. And based on those two, we set up our tokenizer, which we're gonna use to tokenize our tweets into IDs. There's gonna be two additional tokens that you're gonna use, the classification token and the separation token, and you can check their IDs right here. But essentially, we're just gonna say that for the model that it's a classification task and where the separation occurs. Now this function right here is gonna tokenize our tweets, and after tokenization, our tweet's gonna look something like this. So a tensor of the indexes, not of the words, but of the tokens. So when I say not words, what I mean is that in our simple neural network example, when we tokenize the tweet, we saw that each word corresponds to a specific index. Now in BERT's case, we have different kind of tokens. A token can be a letter, a character, it can be a combination of letters. One thing to note is when you want to check out how the model actually tokenizes the tweet and you want to understand it, there's a way of reading it. So if the letter doesn't have these hashtags, I guess, if you would just comment it down below, I would really appreciate. But for now, let's just say it's a hashtag. So if a symbol doesn't have hashtags before it, it means it's a start of the word. So here you see I, then you see that the second word starts with F, which stands for found here, and then everything in the middle of the word has hashtags in it. Then another word starts with O, and you see that is without hashtags, and so on and so on. Some separate words, like the and they, will share a hashtag made up of 3 characters, here and here. But essentially, no hashtags in front, that's the start of the word. Hashtags in front, where something before that character. Cool, so we tokenize our words. How that looks? Well, this is a visual representation of those tokens. On the x-axis, we can see the length of our tokenized tweets, and on the y-axis, they are just tweets. So first one, second one, third one, fourth one, and so on. Now different colors denote different token IDs, color is selected on the ID of the token. Here in the front you'll see that the first one is the same color and looks like empty because it's the same color as background. That's because we added a class token in front of it. Now as for all the other tokens, you'll see that we are different in color just because the IDs are different. All it shows for us is that our tweets were tokenized. Now, after doing the tokenization, we still need to add 2 more inputs. So mask and input type. For the input mask, we just denote everything that is not padding as input, as shown here. So everything in yellow is input. Again, y-axis is the tweets themselves, and x-axis is the length of the tweet. And for the input type IDs, the only thing that is different from this one, you'll see there's a small little line here which represents the classification token, and the actual inputs, the actual words, let's say, will be denoted as a segment of input. You can see that there's a little line here by printing out the input type IDs, and you'll see there's a 0 before each of the array here in the tensor. Having said all that, again, you wouldn't usually do all this in this way. As you want to iterate your training, you should make a function. A function which turns your inputs, your actual tweets, into inputs you're gonna use for the model, so the tokens, the mask, and the type. For that, we're gonna need to pad our tweets to make them equal size, just as we did with a simple neural network, and we need to figure out the length of our tokenized tweets. Since our tokenized tweets don't really consist from words, but more from combination of characters, the maximum length won't be the same as for a simple neural network. We can check the maximum sequence length by just going through the input word IDs and getting the maximum length, which is in this case is 160. And then just to be safe, I usually make it 1.5 times more, and that amounts to 240. Now, what that 240 will mean to us, it will be our set size for both how we prepare the inputs and how we build our model. In the same way as we did in the simple neural network, when we prepared our model, we said that the input size is 180, I think. And whenever we input a new tweet, which we want to be predicted being positive or negative, it can't actually be bigger than 180 words long. In this case, it's gonna be the same, but just in tokens. So, since we have our maximum sequence length already, we make up a function out of the things that we did before, so encoding of the text within the tweets, and then turning that into 3 separate inputs. So the input word IDs, which are the tokens, input mask, which just masks the input, and then the type IDs, which we discussed just now. It's not really that complicated. All this does is makes an array for each of the inputs in the same way described. So we get the tokens from a tokenizer, we add those here. We get the input mask then from those tokenized inputs, which is here. And then we get the segment IDs, which is here. So after having written our function, we just want to finish pre-processing our training and testing data and give that out to our model. So we turn our training and testing data each into those 3 inputs, and for that we use the tweets themselves, denoted here as xtrain, then our tokenizer, which we built from the previously downloaded BERT model, and then we use our maximum sequence length for padding, so all of our inputs would be equal in length. After that, we are finished with data processing and we can move to modeling part. And the things that we need to establish before modeling are pretty much the same as with the simple neural network. The number of the classes, which we're gonna use on our predict layer right here, and the maximum sequence length, which we're gonna use to establish the size of our inputs right here. So we have 3 input layers, as I said before. Those correspond directly to the inputs that we just made. Then here you can see that we use BERT layer to get 2 different layers, a pulled output and a sequence output. There's a difference between those, but just to make it more simple, for this case we use a pulled output and you should use that one too. So we set our output, that pulled output, and we add a dropout layer. A dropout layer helps us with our training, and as we saw from the simple neural networks case, model tends to overtrain on this specific data. Then we set another dense layer right here, and this is our predict layer. So we set our number of classes and we change our activation to softmax. Now you can see here a graph representing our model. Is it really this graph? Well, no. Within this keras layer is our BERT model, which we downloaded, and that one is quite a bit bigger than one layer. But since we downloaded it and are using in creation of our model, it is represented just as one block layer here. As you can see, we have the 3 input layers, then the downloaded BERT model, then a dropout layer for overtraining, and then a dense layer for class selection. Now you might ask, can we add additional layers? Yes, we can, but for tutorial purposes, we shouldn't go too much into that. Now all we need to do is set up the training parameters and we will be able to go and train our model. So here we set our epochs If you remember, epochs essentially are the times the model will go through all of the data it's given. Batch size, the increments in which the model will receive the data. As mentioned here in the comment, select that based on your GPU resources. The bigger this is, the more resources it requires. At some point your GPU will be maxed out and you won't be able to run your model and you will be out of memory. If that's the case, just lower the batch size and at some point you should be good to go. And again, on the imports, check if the printout says that your GPU is available. If it's not, change the runtime. Cool. So we set up our training variables and then we just compile our model. And here in the printout, you will see pretty much the same that you saw in the graph before us. But the thing here, which is mentioned, the total number of parameters, well, essentially the total number of neurons that you're gonna use is 177.8 million. Now, if you would compare that to a simple neural network that we used before, this one had 11.7 million neurons. So essentially, more than 10 times bigger network will be used on the same data, and we'll see how much better the result can be. With simple neural network, we got, I think, 78.5 accuracy. What I'm expecting from this is, after the initial training, to have at least 80. Well, I'm pretending to be dumb, I already ran everything, it is 80. But yeah, what we are expecting is just to get a much better result. This is why we are using a much more complex model. So here we run the training. As you can see, one epoch of training takes around 2200 seconds, which is more than half an hour, which is why we use only 5% of our data, just because we want to test our models quickly and just iterate by trying out better learning rates, different data, and so on. So after training our model for 3 epochs with 5% of data, we get that our testing accuracy is already almost 83%, which is great because it's higher than simple neural network, it's higher than our logistic regression, and it's higher by quite a bit. Now, of course, as always, to visualize it better, we use plot. And here on the left side, you can see the training and validation accuracy, and on the right side, you can see the loss. So the interesting thing here is that the same as with simple neural network, after the second epoch right here, you see that the loss on the third epoch went up. What that means is that our model is overtraining again, and it was the best model we had on the second epoch. You would think that it's fine because the accuracy from the second epoch here to the third epoch here went up for validation as well as for training, of course. But the thing is, you always need to check the loss as well. Just relying on accuracy alone when training a model isn't really a good approach, and this is why loss is important. Now, having said that, is this the end of our model? Almost 83% accuracy rating, the end and the best we can achieve? No, not really, no. We only used 5% of data. We still have other 95% of data to train our model on. What we can also do is change our learning rate, and we're gonna do just that. We're gonna add some additional data and we're gonna change our learning rate and try to achieve a bit better accuracy and see if iterative training of our model could actually work. So what we do here is we save our model for later use. So since we already trained our model here for 3 half hours, which a bit more, so around 2 hours, let's say. We want to save our model because we don't really want to train it from scratch again. We want to have the one that we already trained and then fine-tune it a bit more later on, let's say in the next working day. So what we do here is we recompile our model. Essentially, we just change the optimizer to my name, and we do that because with custom optimizer, that we used before with weight decay, we can't really save our model. I don't really know what that error is, I don't really know how to fix it, so what I do and what I suggest for you to do, find a workaround and use that. So we save our model, we just check the name of the model that we want to save, the directory in which we want to save the model. We save it by just saying model.save and then the path where it should be saved. It saves it, and then let's say a couple days passes, we want to get back to our model, we want to fine-tune it a bit. We jump into import, we import all the packages that we want to use, we jump into data and we read our dataset. And then we can just read our model, we can validate if it's not corrupted in any way. Always when saving a model, validate it at the same time, just because sometimes it can go wrong and it might corrupt some files. And not only the model itself, but also the tokenizer. Just to be sure, if this loads up and then tokenizes the tweet, you're fine. It will tokenize the tweet in the same way, you don't really need to check that up with the tokenized tweet that we did before, because if something went wrong and it didn't save the model correctly, this won't just run at all. So after checking all of this, you are good to go to load your model in a couple of days, and let's say those couple of days pass by, you want to train your model again. You check these graphs again and say, okay, so the second epoch it went sideways and the loss went up. I want to train it a bit more. You have your model, you decided that you will add another 5% from your dataset as your training data, and you will lower your learning rate because your model is already a bit trained. Now, for those of you who don't really know what learning rate is, so neural network has a bunch of neurons, and those neurons have weights associated with them. Each of those weights impacts the loss of the model, right? So imagine a graph. So each of those weights impacts the loss. So imagine that here on y-axis we have the loss, okay? Here is loss. Cool. And then the x-axis we have the weight, which is associated with the neuron. So there's some weight out there, which is this weight, which value we don't really know, well, at least at this point, which is the best weight for the loss, right? Which makes that loss minimal here, right? So this is the best weight that we can have. Now, what our learning rate is, it's the speed at which the weight changes. So each time we run our data through the model, during backpropagation, it adjusts its weight based on if the answer was correct or not. So it always tries to optimize this. It always tries to move the weight into the position where the loss is minimal. So here, right? So this is the min loss. Oh my god, I really need to get some writing classes. So this is the minimum loss. If our learning rate is 1, what is going to happen? It's going to move the weight, let's say from here to here, right? And our loss didn't improve. And at the start of training, a high learning rate is actually quite good, because it gets your model going and it adjusts the weight quite fast. But when you already train your model for a bit and you see that your loss is going up again or is stagnant, what you need to do is you need to decrease the learning rate. Why? Well, if it's a 1, if you would make it to 0.5, it would move from here to here, right? And that's actually where the minimal value of the loss is. So if this one is 0.5, it moves the weight but into the minimum value. So again, just to be short, when training your model at the start, use a bit higher learning rate and then use a bit lower one on the second and the third iteration or how many iterations you're gonna do, just to decrease the speed at which the weights are changed, so the model could optimize itself a bit more precisely. So we're gonna do exactly that. Okay, we went through those. So data, we already read the data set. What we want to do now is make a different training and testing subsample when we had before. So we just changed the random states and bam, we got our new data. Just to be sure that our sample collection is random, we can check if the plot of distribution of the classes again looks the same as previously. It does, everything's fine. For the label encoding, we already saved our encoder before. All we need to do now is just to load it again, and we'll have our label encoder. For inputs, we can make our tokenizer from the vocabulary file of the saved model that we saved after training. And here it is. All we need to do is just set that lowercase as false, as it is with the model, since it's a cased model, and good to go. We have our tokenizer now. So we don't really need to run any of that code before, just the import and the data read. Then I just repasted the input preprocessing function here again. So just use this function to prep our inputs once again right here, and then we can train a bit more. So this is our model. We read our model from the saved file, we print it out, we see that it's the same model, we have the same maximum sequence length and the same input size as before. This is the picture of the model, same as before. And then we can check how different the data is. So we have now an xtest1 and xtest2. xtest1 is denoted as xtest and xtest2 as xtest2. And after checking our model, both of those datasets, you'll see that our model performs better on the new dataset. So our datasets are indeed a bit different. To be consistent when training the model for a second iteration, what you want to do is to use the same testing dataset, just to be consistent and see the changes for the actual changes. So what I'm saying here, don't forget to save your testing dataset. Then we set our training parameters again, same number of epochs, same size batch size. So the only thing that we change is the learning rate for our optimizer. Our optimizer is actually using weight decay, so the learning rate goes down over time by itself, but let's not get into that. In this tutorial, I guess we'll just keep it for later. We recompile our model. Remember, we changed our optimizer to Adam, me, when saving our model, and now we want to rechange it back to our new optimizer. And after this, we can do another training session. So as you can see, the training takes essentially the same amount of time. Again, all we do is use new data here, but we use the same data for validation. And then if you plot everything out, what you will see is some great news. So at this point, we had already trained for 3 epochs. So right here, wait, give me a sec. So we already trained for 3 epochs. So here, this is what we already had, and same here. So this is training session 1, and this is training session 1, and this is training session 2, training session 2 as well, right? So what we saw here is that validation accuracy actually went up both from first to second epoch and from second to third, but the loss broke at second epoch here. Now, after training our model for another 3 epochs, we see that the validation accuracy increased in every successive epoch here, but the training accuracy dropped significantly when we introduced a new training dataset, and then it went up again bit by bit. The good news here is, what we see is that our training loss separation and validation loss separation, well, it's another way around, but training loss, validation loss, our separation is the same as we had it here, but this time our validation loss was quite stagnant, meaning at this point the model is not overtraining as much as it did after the second epoch on the first training session. So it's a good thing. We have a better model. And by how much a better model? Well, we can check the accuracy again. So if we would go to evaluation, did we do that? No, we didn't. Doesn't matter. We can go here. It will give us the same. So what you can see here, now our model predicts at 83.66% accuracy. And what's more, I think that at this point we could add additional 5% of data and then train the model for additional 3 epochs. We could try lowering our learning rate again, but I think the additional data would help us a lot as well. So since the first training session, we moved up for what? Around a percentage, right? Yeah. So we had around 83 and now we are nearly to 84. So by this point, I think that we could actually, by iterative training, achieve around 85% of accuracy with this model. And you can actually do that. You can use this notebook and then just reiterate iterative training, and you should get to something like 85% with this. So at this point, the main question here is that additional couple of percent of accuracy is worth it? So let's look into our models. Our logistic regression had a 0.8 accuracy. Simple neural network, pretty much the same, right? And our fine-tuned BERT, after 2 training sessions, has almost 84% accuracy. I ran it a couple of times, so it might be off a bit. But yeah. So the thing is, it all depends on you. And as far as this tutorial goes, you're good. You know how to fine-tune a BERT model. Either download the notebook or just go to a Colab link in my GitHub, and the link to that you will find in the description. But as for our further investigation, how we could improve our accuracy on this model, on this task, or what else could we do, there's quite a good question to ask ourselves at this point. Like in any project that you're gonna do with machine learning, you need to think of a couple of things when thinking about deployment. In a lot of the cases, I would say that just go with logistic regression, because it's already at 80% accuracy. We did the same test with it. It works just fine. You won't have any issues, and the biggest advantage of logistic regression is it's fast. It doesn't really take much time to give out an answer with it. And you don't need a GPU, you don't need anything. You can implement it in a simple web page. Now, simple neural network, no. You already have a logistic regression with a better accuracy than the simple neural network, so just go with that. Now, when we compare fine-tuned BERT with logistic regression. The main question is, what is more important to you? Is it more important resource-wise, that it would be fast and that it wouldn't cost much to run? Then surely go with logistic regression. But if accuracy is key, then go with fine-tuned BERT. And if you think that accuracy is key for your application, that 4% increase of accuracy has much more weight than the amount of resources that you're gonna save using logistic regression instead of BERT. What I would suggest then is to do a modified version of BERT, add additional variables to it. Let's say, like in this example here, we have date. And maybe date of the tweet, let's say a weekday, or the time impacts the sentiment of the tweet. You could add those additional variables to the BERT model itself. And instead of this with 3 inputs here, 1, 2, 3, you could add an additional input right here and make it like time. Let's say it's time. Oh my god. It's good that I do machine learning tutorials and not drawing tutorials. Okay, it's time. You're gonna get it. Time. And connect that to this layer here, or just, append it. And do your decisions from that. You could add additional dense layer here, right? So this is what you're gonna do next week. We're gonna add an additional input layer. We are not going to add an additional dense layer, but just to keep in mind, if I forget to add this next week, since you're adding an additional layer of input and you're just appending that to the pulled output from BERT model, it could be quite a good idea to add an additional layer between the predict layer and the pulled output with the appended new variable layer. So having said that, that's all for today. Now you should be able to fine-tune a BERT model. I hope that most of the things that I said made sense. As always, some of the code is mine, most of the code is from internet, but I guess you can use it freely. If you make something fun out of it or not, or even if you have some problems making something, leave a comment, write me on Twitter, Instagram, Discord, whatever, and I'll try to do my best to help you. And for the next week, we'll do a modified BERT model with additional variables. And with that, I say goodbye and see you really, really soon. Bye.